we talked yesterday what the cosine double angle generates for us in regards to the half angle. We said yesterday if we start with cosine of 2x, that is equal to, using the double angle formula, that is the same thing as 2 cosine squared x minus 1. And we recognize right here that there is a 1 to 2 relationship. So this is a half angle right here of what we start with, correct? Does that make sense? So if this is 30 degrees, this would have been 60 degrees. If this is 100 degrees, this would have been 200 degrees, right? Okay. So what we went through yesterday is just making a simple substitution of basically renaming our variables. It's not changing anything other than that, other than defining your variables a different way. So if I just say theta is 2x, then x is theta over 2, right? Theta over 2. And then we just replace those things. So it came out to cosine of theta is equal to 2 cosine squared theta over 2 minus 1. It's still the same thing. If theta was 200 degrees, isn't this still 100 degrees? If theta was 120, isn't this still 60 degrees? Does that make sense, everybody? Okay. So it's just a redefining of variables to make it look and make it more obvious that this is half an angle. Okay. So then we solve for cosine of theta over 2, and that ends up giving us cosine theta plus 1. Okay. That would, be that. We then divided by 2. So that 2 would have gone away. Okay. And then we took the square root, and that ends up giving us cosine of theta over 2 is equal to plus or minus cosine theta plus 1 over 2. And what we have to do there is make sure that we are aware of the quadrant that the half angle is in. And that's going to tell us to choose the plus or minus there at the beginning. So that's cosine. Well, what we're looking at in this problem is sine, right? And we didn't talk about that yesterday, but the formula is in the PDF or on any of the PowerPoints that you're maybe using from my website. But it's generated the same exact way because the cosine of 2 theta is also equal to 1 minus 2 sine squared theta, right? That's an alternative version of the cosine double angle. If I go ahead and make the substitution that, instead of using theta, let's use x just to keep it aligned with what we were doing in the last one. If I say theta is equal to 2x, then theta over 2 is equal to x. So now I just plug that in. Cosine theta is equal to 1 minus 2 sine of theta over 2. And now what am I going to solve for? Sine of theta over 2, right? That's what we want, the sine of that half angle. So I subtract 1. It's going to give me, this is squared, so it gives me negative 2 sine squared theta over 2. Divide by negative 2. So it's going to change those signs, so it gives me that. Then I square root both sides, right? So it gives me sine of theta over 2 is equal to plus or minus the opposite of cosine plus 1 over 2. Now, a lot of times we write that as 1 minus cosine. And it's cosine, I do this from time to time. The more I work with these trig functions, the more I forget to put in the argument. Okay? But that's your sine half angle formula. And again, what we need to do is recognize what quadrant your half angle is in so that we choose the right plus or minus. Okay? So, that being said, they are asking us to use that with this. Now, what would you guys prefer? Would you prefer to work with radians or would you prefer to work with degrees? Degrees. Okay? So, take 11 pi over 12 and multiply it by 180 over pi. Okay? And that's going to give you whatever 11 times 15 is. 165. Okay? 165 degrees. Is that okay? Okay? So they're asking the sine of 165 is equal to what exact value? Okay? And we can type that in our calculator and get a decimal, and a decimal is going to be the same as what this is. But the best way of writing this is to say it's the sine of, now if I take 165 and double it real quick, I get 330. And I'm going to write that over 2. Do you recognize now how I've written that as a half angle? As a theta over 2? Okay? So we said that the sine of theta over 2 was equal to plus or minus, okay, 1 minus cosine theta all over 2, right? Okay. Now, the 165, okay, is our theta over 2. Does that make sense, everybody? What quadrant is that in? Second quadrant, right? The sine in the second quadrant is what number, or what kind of number? Positive. So that's why we take the positive version of this, okay? Now, the ultimate reason of writing it this way is to realize that this 165 is theta over 2. We don't use that in this expression over here, right? We use theta. So doesn't it make sense to write this as theta over 2 that way? And now can you see directly that that's a 1-to-1 relationship? 330 over 2 equals theta over 2. So does theta have to be 330? Okay. So that's what we're plugging in on the right-hand side here. Cosine, or 1 minus cosine of 330 all over 2. Okay. So now, what is the cosine of 330? That should be something that we're aware of, something we know. I'm on the unit circle. Okay. 330 should be about right there, right? Okay, almost there. 330. I would need 30 more degrees to get there, right? So it's referencing an angle of 30 degrees over here, right? The cosine of 30 degrees is what? Radical 3 over 2. So the cosine of 330 is going to be the same thing. So 1 minus radical 3 over 2, then all over 2. Okay? Now, you could probably type that in, and I would assume that WebAssign is going to say, yeah, that's fine. Okay? But if I want to maybe condense this, we'd have 2 over 2 minus radical 3 over 2 all over 2, right? So it gives me 2 minus radical 3 over 2, all divided by 2. Okay, well, what do I do with a fraction divided by a fraction? Multiply by the reciprocal. So it becomes 1/2 up there, right? So now I'm multiplying that through. Distribute your 1 through. Still gives you 2 minus root 3. Now you're going to 2 times 2. It gives me 4, right? Now with our laws of exponents, we should know that we can break that apart as the root of 2 minus root 3 all over root 4, right? What's root 4? 2. And that's exactly what then they have as their final answer. Now, what we end up doing is some people want to say, well, you got a square root right there. Well, because there's a difference in the numerator, you don't go any further. You can't go any further. Okay? That's the most simplistic way of writing that. Okay? At least with the current expression, current understanding we have with radicals and all that kind of stuff. Now, we also found that, I think, sine 11 pi over 12, 165 degrees, I think that is also radical 6 plus radical 2 all over 4. Okay? So there is an alternative version of that number using the sum and difference formulas. Okay? Because I'd take, to get 165, could you take maybe 120 plus 45? that make sense? And that will give me the same thing. Okay? Now, like I said, it'll give you like radical 6 plus radical 2 over 4, something like that. But those two numbers should be identical. Does that kind of help? I think the biggest issue people have with half angle formulas is not knowing on that inside part, okay, not knowing whether we put the 165 here or the 330 here, okay? A lot of people put 165, and obviously that messes everything up. Okay? All right. Any others? All right, so we're looking at cosine of 165. Okay, so this is 11 pi over 12, right? That's the same number we just dealt with. So now we'd be looking at the cosine. If I'm going to use the appropriate half angle, I'd be looking at cosine of 330 over 2. Okay, now kind of understand something here. As we're working with these and trying to learn the half angle, they will undoubtedly tell you use the appropriate half angle formula in the directions, right? Later on, okay, when we get into maybe calculus and we have to use half angles or whatever, they're not going to tell you, okay? It's just going to be something you have to know. It's kind of like in Algebra 1, they told when you're first learning how to factor, they would say, factor this using the AT method or factor using grouping techniques, right? Okay? Then eventually in Algebra 2 and college algebra, it was just expected you knew how to do that when you came across it, right? So eventually there's going to be kind of implied mathematics that we don't get a direction stated for us, okay? So if that were the case, maybe in a calculus class you'd say, well, I can find this by taking a sum and difference of cosine, and then somebody else might say, well, I can find half angle, okay? And there are things in calculus that we do with some of our integrals that the half angle formulas are very important to us, okay? So it is essential kind of to know these things. All right, so when we do the cosine of theta over 2, that is equal to plus or minus. Now it should be 1 plus cosine theta over 2. Okay, 1 plus cosine theta over 2. So again, we got to think about what quadrant the half angle is in. What quadrant is 165 in? The second quadrant. So I'm going to take the negative version of this root. So it'll be negative roots. Now it'll be 1 plus cosine of theta, which if this is theta over 2, theta is 330, right? So cosine of 330, then divided by 2. So we've already said that 330, the cosine of 330 in the last question was radical 3 over 2, right? So we get that. That's all underneath our root here. So coming up with, simplifying that fraction up top. Again, I think, because WebAssign usually does this, WebAssign is usually pretty lenient in the simplifying process. So they usually, I think, would accept this. Okay? But I think we have the algebra skills that we can go through and say, okay, well, this is, that 1 is 2 over 2 plus root 3 over 2. So it's going to be 2 plus root 3 over 2. That's what that numerator becomes, over 2, all under the square root, and it's opposite. Now, just like the last one, we're going to multiply by 1/2, right? Get rid of this fraction here. And that gives me a 4 down here on the bottom. This gives me root 4. And we know we can break that up into 2 roots. So now what's root 4 turn into? 2, okay? So now this, and this is the thing that I think we need to know, we need to visualize, if I were to do this problem wrong and all my work looked like this, and then they give me this feedback, okay, I hope we understand those are the same, right? All they've done here is factored out a 1/2. So I have 1/2, and then times root 2 plus root 3, okay? Well, if I consider this root 2 plus root 3 over 1 and multiply that back out, doesn't it just get this? Okay, so they just, and they're, I don't know if it's like a coding process that they have that is just kind of systematic for all the questions within WebAssign. But a lot of times when we would by hand write something as negative root 2 plus root 3 all over 2, for some reason their feedback is always factoring that negative 1/2 out. Okay, which is fine, but I think we need to understand that those are the same thing. Other ones? We can do as many as Irene? 15? 19? On the day 2 or day 1? Day 1? Okay, simplify the expression by using a double angle formula or a half angle formula. Okay. So we've got squared of theta over 2 minus sine squared of theta over 2. Now, what happens here is that is, I don't really care so much about what the argument is at the moment. As long as it's the same, I think that matters. But if I were just to say cosine squared of something minus sine squared of something, if we go through all of our identities that we have, okay, that is one of our double angle formulas. Let me bring up the notes. Or actually, let's kind of do this. Let's look at that formula sheet. All right, so if we're looking at our formula sheet, kind of scroll through, what we're trying to do is see if what they gave us matches kind of any of these sides of our formula sheet. So I keep going through. It's none of these. Turns out to be this one right here, right? Sine double angle. So it says whatever the argument is, x and x, this becomes 2x, right? So if I'm looking back, maybe using the notation we were using here, this is cosine of 2 times whatever that question mark is, right? Well, that question mark for our particular problem is theta over 2. And now if I plug that question mark in here, what's cosine of 2 times theta over 2? What's that going to give me? Cosine just theta. So that's what they're trying to get us to do, is recognize that even though the argument is half of a theta, half an angle, the expanded version, the setup between cosine squared and minus sine squared, is a double angle concept. Same thing there on that bottom one. Okay, that was, so 2 sine of something, cosine of something, that is equal to 2, sorry, not 2, that is equal to sine of 2 times that something. Well, that something here is theta over 2, theta over 2, so then when we put theta over 2 there, so it gives me sine of theta. Okay, so those are additional identities. Now I don't know that we would ever use these because we have better ways of finding sine theta. But if you wanted to check to see before you typed in cosine theta, sine theta, or if this is on a test before you wrote it down and finalized it as your answer, we should be able to kind of see if this makes sense. By using, I'm just gonna put it in degrees here. Let's go. Let's write, cosine squared, and let's just say, let's put s over 2. Okay, minus sine squared of the same s over 2. Now, it doesn't matter if you use s or t. I just kind of want to stay away from x and y. I think if we did x and y, we'd probably see it graph being the same. But we get that thing there. And now, because I'm in degrees, I'm just going to go from negative 360. I'll just go from 0 to 360. Okay. So if I run back through there, obviously we're getting those quantities, right? So then the question is, well, does that give me the same thing as what we found out to be cosine of s? Okay, so we're seeing then, as I move this slider, is it going to evaluate these two things the same way? And if it does, all the time, then we've proven that we do indeed have that identity, right? We have changed that thing correctly. If I were to just graph, let's see what, putting x here and x there. Now, it looks like just a line because I am in degrees, so radians will give me that. Okay, and then if I graph, does that look just like the cosine of x? Yeah. So you can either do the substitution with specific values and make that slider kind of substitute all those values that you want, or you can use the graph, and the graph kind of simultaneously tells you all of those solutions are equal at the same time, or all those like those two curves are equal all the time. If we do the same thing with what was it, 2 sine of that cosine of that, does that look just like the sine of x? So that's kind of a validation, I think, graphically that we have the right identity. And I think, guys, that is a huge principle to kind of abide by when you're doing these types of evaluations or simplifying identities, is to graph your final argument, your final statement, and then graph your original one, and make sure that they are the same graph, right? If they are, it at least tells you that the two things that you have are equal, that they are the same. You haven't made any mistakes there. It does not tell you that you are fully simplified. Does that make sense? Okay. But hopefully that's something we can gauge as well, kind of on our own, just by looking at what is left over. Okay. Other ones. Yes. Number 8 on 1. Okay. Okay. So this is the one new angle that the half angle formula actually produces for us on the unit circle. The double angle, we say, okay, if we know the 15 degree, then we double it, we get 30. That's not new. Take 30, double it, that's 60. That's not new. Take 45, double it, that's 90. That's not new. Take 60 and double it, that's 140. That's not new, right? So all our double angles just kind of gave us points on the unit circle that we already knew the ordered pairs for, right? But this one is a new one because it's currently, if I take all the 15 degree increments across the unit circle, is there anything to do with those to get 22.5? There shouldn't be. Okay? But with a half angle formula, what number am I taking half of to get 22.5? 45. So I take half of 45. Now I'm going to be generating a new ordered pair on the unit circle for an angle that I was not familiar with to begin with. Okay? So when we go cosine of 22.5, we're going to write that as cosine of 45 over 2. The reason we want to do that is because now the 45 is the theta that needs to go into our formula here. Okay? And the cosine formula is plus or minus. Okay? It's 1 plus cosine theta all over 2. Okay? I'm a, again, and I told you this before, if you were to ask me 3 days ago what the cosine half angle formula looked like, I could tell you that it's the square root of something with cosine and 1 on top and 2 on bottom, but I couldn't tell they told you that it's plus cosine. Does that make sense? Because the other one is cosine minus 1. And they're so similar that I get them confused all the time. But I could have also told you 3 or 4 days ago that the cosine half angle comes from the cosine double angle identity. And I could work through real quick that double angle identity, which maybe if I didn't know the double angle identity, I know the sum of cosine of theta plus theta. So I can work my way backwards through identity to find out what this one is when I don't have a reference sheet, or somebody asks me quickly what is it and I haven't used it in 8 months. Does that make sense? Okay. So I think it's hard to try to memorize. Let's look at these here. If we look at the half angle formulas, I mean these two versions, the sine and the cosine, they're very similar, right? Okay. I forget which one is 1 minus and which one's 1 plus. Okay. Maybe you can remember because sine has an n in it and minus has an n in it. Cosine positive doesn't have an n in it. Positive doesn't have an n in it. Does that kind of make sense? I don't know if that would be a device that you could use to help remember which one's plus, which one's minus. But nonetheless, we're using the plus one here. Okay. Now we got to think about what quadrant 22.5 is in. Obviously, that's the first quadrant, right? So we'd be looking at 1 plus cosine of 45 degrees all over 2. What's the cosine of 45? Right equal 2 over 2. So we get that. So this 1 is going to turn into 2 over 2. Okay. And that numerator is going to turn into 2 plus root 2 over 2, right? 2 plus root 2 over 2. That's over 1. We're going to multiply by 1/2. So it's going to give me 2 plus root 2 over 4 all underneath the root, right? But what's that 4 going to turn into? That root 4 is just 2, right? And if you want to, here, WebScience not doing it. If you want to factor that 1/2 out and write it as root 2 plus root 2, or the root of 2 plus root 2, you can do that. Either one of those is fine. And like I said earlier, I think they probably accept the square root of 1 plus root 2 over 2 all over 2. So now, what that is, guys, if we were to just kind of piggybacking this stuff all off of what we've already talked about in the past, if we get to the unit circle, so I go x squared plus y squared equals 1. And these are all little relationships that we can use to check to make sure what we're doing does make sense, that what we're doing is right. We said the angle should be 22.5, right? I think I just go divided by 2. Okay. Now what should happen here then is that this ordered pair right there, if we show the name and value, should be that number right there. Okay, 0.92. Go out a couple more decimal places here. Okay. I don't know if this will work. I don't know if this probably isn't going to give me what I want. x of a prime. Let's see what that just spits back. Yeah. So if we take in the square root of 2 plus the square root of 2, so that's all underneath the radical, and then multiply that by a half, that's what we came up with. Okay, let's see what that gives us. Gives the same 0.92 number, right? And that's what cosine is. Cosine is the x value of something on the unit circle, right? Does that kind of make sense, everybody? So right now, this ordered pair is root, let's write it this way, it'd be positive root 2 plus root 2, all over 2, comma then, let's work through what the sign of this thing would look like. I'm going to use the sign half angle formula for 22.5. That's going to be sine of a half angle is equal to plus or minus. Now, sine is 1 minus cosine theta over 2. And now because we're in the first quadrant, we're obviously looking at that sign being positive, right? And now if I go, well, 22.5 is the same thing as 45 over 2. I would now have 1 minus root 2 over 2 divided by 2, right? And that should be, once we evaluate that, it's going to give me the square root. Let me see if I can just cut and paste this number here. Control C. Control V. It's going to give me that thing there. But instead of being 1 plus root 2 over 2, it's 1 minus root 2 over 2. So the only thing that changes, that's going to be a minus. And if I evaluate that, it gives me 0.38. Does that kind of make sense to everybody? So this ordered pair for 22.5 is that. Okay? Now, obviously, those are messy looking, right? So hopefully you realize, that's not like 1 half comma radical 3 over 2. So maybe you see why we don't memorize those off the unit circle. And also, how many times have we think about all the questions you've done so far in this course, how many times have you dealt with 22.5 degrees? Probably not very often, right? So it doesn't make sense to know that. But you've dealt with 30 degrees, you've dealt with 60 degrees, probably hundreds of times already. Okay, so it makes sense to remember those off the unit circle. So now we got 22. So now I know those. Can I now divide 22.5 by 2? That makes sense? Okay. So what the half angle formula does is actually provides an infinite number of ordered pairs on the unit circle. Because I can start taking every single ordered pair that I know, every angle I know, and cut it in half however many times I need to. If I looked at 30 degrees, cut in half, I get 15. Take 15, cut it in half, I get 7.5, right? Take 7.5 degrees, cut in half, I get 3.25. Cut that in half, I get, 1 point, whatever, I don't know what it is, 1.715, something like that, 125. You can cut everything in half over and over and over as many times you need to, right? So it's going to produce ultimately a lot more ordered pairs than what maybe our other formulas are generating. Any others? Those first few are double angles, double, half. All right, so let's talk about the tangent double angle formula here. Okay, if we go through a little bit of work trying to find, let me find a blank page here we can work on. If we want to find the tangent of theta over 2, we should know that is the same thing as sine of theta over 2 divided by cosine of theta over 2, correct? And if we go plus or, so the sine is going to be a plus or minus radical, right? And so is the denominator. So as we work through, because you got plus or minus divided by a plus or minus, that's ultimately, in any orientation that you can come up with, will be a plus or minus, right? Okay. Eventually that plus or minus will kind of fall out. We won't pay attention to it. But then we do have to kind of, because the square, and it's a little bit different than what here, because we had to choose plus or minuses here, right? The tangent u or 2, if we know where u is, okay, and we choose the right sign with u, the tangent of u or 2 is going to kind of work its way out to be accurate, okay? So, and the reason this goes away here in a moment is because of some multiplication that we have to do. So sine of theta over 2, okay, that is 1 minus cosine theta over 2 times 1 minus cosine theta over 2, right? Okay. Now, just to kind of understand, and this is all because of our laws of exponents, can't I write that top one as 1 minus cosine theta all over root 2? Does that make sense? Can I write this bottom one, oh, sorry, this one's a positive. Can I write this bottom one as 1 plus cosine theta all over root 2? That makes sense? You got fractions inside a root, you can separate them, right? So what's going to happen with these root 2's? Yeah, I have fraction divided by fraction. I'm going to multiply by that reciprocal, right? And ultimately multiplying by that reciprocal when the denominators are both the same, really those just wipe out, and you're left with 1 minus cosine theta over 1 plus cosine theta. Is that okay? Now, we know that to be the same thing as this. 1 minus cosine theta over 1 plus cosine theta. Is that all right? Now, that looks a little bit like our identity. Okay, but not quite. A little bit, but not quite. Okay? Our identity for tangent doesn't have roots in it, right? So the way we actually get those to go away is that we multiply by conjugates here. Okay? And it doesn't matter which conjugate you want to multiply by. But let's say I want to multiply by 1 minus cosine theta. Multiply by that top one's conjugate. 1 minus cosine theta. Okay? When I do that, this is all underneath the root. We're doing this all underneath the root. Okay? I multiplied just by 1, right? The radicand? So that's fine. But what's that numerator? Could I FOIL that numerator out? Alright? You could. But in this situation, that's kind of a silly thing to do. Because it's underneath a square root, isn't it? Okay? Now when I multiply the bottom out, let's multiply that bottom out. Because they're conjugates, right? Okay? They're conjugates. So O and I are going to cancel each other out. So you're left with 1 minus cosine squared theta on the bottom, right? What's 1 minus cosine squared the same as? Sine squared. up top, you've got that. On the bottom, you're going to have that, right? What happens with those radicals and the powers of 2's here? Cancel out. So you're left with 1 minus cosine theta up top, and you're left with sine on the bottom. There's your, and that's the really nice thing about the tangent half angle, is that there are no radicals in it, right? They all drop out because of that conjugate process. If you were to work with the, so we chose the conjugate of the denominator, right? 1 minus cosine theta. If we were to look at multiplying by, and I think we can actually do it several different ways here. Let's just kind of start at the point where we had 1 minus cosine theta over 1 plus cosine theta. So starting right here, we multiply by the conjugate of this one here, right? Let's multiply by the conjugate of the top. So let's multiply by 1 plus cosine theta and 1 plus cosine theta. So on the bottom, it's going to give me 1 plus cosine theta squared, right? Up top, if I multiply those out, I get 1 minus cosine squared, right? 1 minus cosine squared. What's 1 minus cosine squared the same as? Sine squared, right? Well, square root of sine squared. Sine, and then I look at this, that's 1 plus cosine here, right? Okay. So now you can see an alternative version. Now they're not just reciprocals, right? This one's flipped, and then the bottom sign is different. Okay, the plus or minus. That's one way to do it. Or we could have started with like 1. I think we could go with 1 minus cosine theta over sine theta here. Start with that one, and let's just multiply by the conjugate of 1 plus cosine theta right away here. See what happens. If I do that up top, I get 1 minus cosine squared theta, right? 1 minus cosine squared is sine squared theta. On the bottom, I now have sine times 1 plus cosine. What's going to happen with the sine squared and sine? They're going to cancel, right? It means just sine theta up top, and then a 1 plus cosine theta on the bottom. So there's 2 ways of going from that blue one I circled to the second alternative version of tangent. Now, why would it be useful to know the alternative versions of the tangent? I do not know. I don't think, if we look at them together, is there a benefit over this version and that version? I don't think so, because if I want to find tangent of u over 2, let's say I want to find tangent of 22.5. I'm going to use those formulas. Don't I need to know what the cosine of 45 is and the sine of 45? Okay, and regardless of which one of those I choose, I got to know sine and cosine of 45 for both of them. I don't know if there's a benefit of either, but there are alternate versions there. Okay, I will move back the assignments until I'm looking. I'm going to move it back to Monday. Okay, from Monday night, 11:59 p.m. Monday night. So you get a little bit more time on both those. But I do want to continue to, they've been open for about a week now, and some of them have NDs next to them, which means you have not started them. Okay, make sure that we're progressing through the homeworks. All right, so guys, we haven't talked about all of the half angle formulas. So before we get to this problem, let's do that. Okay, introduce those. We introduced one of them yesterday, the cosine half angle, and it was generated by taking the cosine of 2x. We know that identity is 2 cosine squared x minus 1. And I told you last class this, and guys, in the video, if you go back and watch the video, this video is like 80 minutes long. I just continued from last period. Total ad thought that if you would have asked me 2 days ago, maybe even yesterday, not 2 days ago, if I could off the top of my head rattle off to you what the half angle formula is for cosine or what it was for sine, I couldn't have done it. Okay? I don't know what it was. Okay? I know the similar structure or what it should structure as, but I messed the signs up, the SI, GN, and I messed up other components. Okay? But what I won't mess up is the idea that I know that the sine half angle and the cosine half angle come from the cosine double angle. And if I know the cosine double angle, that's awesome, because now I can create half angles, right? But if I don't know the cosine double angle, don't I know that the cosine double angle came from the cosine of theta plus theta? Yeah. Okay? And now this might be a far stretch, but if I didn't know that, I can say, well, there's a geometric proof to figure out what that is. Okay? Maybe I know that proof. So that proof that we did the other day with the circle, and we drew out the arcs of P and S and negative S, and drew the chords and all that kind of stuff, and used the distance formula. Ultimately, that produces all of these formulas. Okay? If I can remember that, the idea is that all of these flow from it. Okay? So in regards to, like, people always ask me, so which one should I remember, which one should I not? Bare minimum, I think if you're going to memorize something, memorize that cosine of alpha plus beta is equal to cosine alpha, okay, cosine beta, minus sine alpha, sine beta, and then the rest of these kind of come from that, okay? So we're going to cosine double angle. We know, or we did this yesterday. Now, these are half of one another, right? So we could actually just solve for x right now and say, well, this is the half angle formula. Let's kind of do that. Maybe it'll make sense to some of us this way. If I just try to solve for this cosine of x right here, so I'm going to have cosine of 2x. I'm going to add 1 to both sides, right? That should give me 2 cosine squared x. I'm going to divide both sides by 2, so that gives me that, right? And I'm going to square root both sides. And it gives me that. Is equal to cosine of x. Okay? Now, that is the half angle formula. Now, what you usually don't see it written that way is because it looks like a 1 to 2 relationship, right? And it's not the way that we usually envision a half for a half angle. But that x is half of the 2x, is it not? Okay. So what they generally do in presenting formulas to you is they say, okay, well, let's let x equal theta over 2, then 2x would equal what? Theta. And now they make those substitutions. Say, okay, well, let's put theta over 2 there for that x. And then we put theta in here for that 2x. And that is our cosine half angle formula, usually the way it's presented. Now, a lot of times they don't even use theta, they use u. And you'll understand in calculus why they use u, because u sometimes will represent another function. So we'll have a nested function here, and we want to use the whole u, not just, you can see theta, just a number or something like that. So we're talking about that. Does that make sense? Some of you might appreciate looking at that cosine x equals cosine 2x, because it tells you that inside that radical, you're going to be using twice as much of an angle as what you're kind of setting out to look for. Okay? So they asked me, what is the cosine of 30? Okay? And inside that radical, I'm actually using cosine of 60, right? If they ask me the cosine of 22.5, then on the inside of that radical, I'm actually using cosine of 45. And what happens is that angle on the inside, I won't say it all the time, but most of the time we see questions with this, that angle on the inside is going to be one of the 45, 30, 60 multiples that we know off the unit circle. Okay? So that's the cosine. Now, the sine there are so many different ways, guys, that we can develop the sine one, but I think the easiest way is if you understood what we just did right here, and we should be able to do the same thing with cosine double angle because it incorporates an alternative version that has sine in it, right? Can I solve that for sine? Okay, so I'm going to go, this is going to look like cosine of 2x minus 1 is equal to negative 2 sine squared x. I'll divide both sides by a negative 2, so I'll make that negative, go to positive, and now I've got a denominator of 2. Wipe that away. And then what do? Take the square root. So it gives me that equal to sine of x. Okay? Now most of the time what they'll do is say, okay, let's say x is theta over 2. And then we go plus or minus here. Okay? It's going to be 1 minus cosine of theta, and that whole thing over 2. Is that all right? There's your cosine, half angle, sine, half angle. Usually, and it doesn't matter, because addition is commutative, right? So that doesn't matter if that's 1 plus cosine or cosine plus 1, right? I think it is a good idea to write it as, if we're trying to kind of remember these things by looking at their relationships and seeing how their structures are kind of similar. Those two structures are pretty much identical, are they not? Except for there's a plus sign and a minus sign inside the numerator set, okay? For the last class, and this is why I don't memorize these things, I mess those up all the time. But if you're going to memorize them, maybe, if I look at the sine one, sine has an in it, and so is the word negative, right? Or minus, okay? So that might help you realize that one, the sine half angle, and the numerator on the right-hand side, you have the minus sign. Cosine has an S in it, and so is the word plus, okay? And that might help you with the positive sign in that numerator. I don't know if that would be useful. I think sometimes those things they work for me, but again, they don't work for everybody. They're maybe harder to remember for everybody else. Those are your half angle formulas for sine and cosine. Now, let's find the half angle formula for tangent. Okay, if I want to find the half angle formula for tangent, we're going to say a tangent of theta over 2 is equal to, isn't it sine of theta over 2 divided by cosine of theta over 2. Do you guys agree with that? Sine of theta, we just figured that out to be plus or minus 1 minus cosine theta over 2. And then the cosine here is going to be 1 plus cosine of theta all over 2. Okay. Now, just because what we know, and this all exists, I don't know if we've talked about this in college algebra or not, but because of our laws of exponents, if we have a numerator underneath the radical and a denominator underneath the radical, can't we put them all underneath the same radical? There's a couple different ways of doing this. I think in the last class we left them underneath the same, or left them underneath individual radicals. And I think in the last class we actually did this. We actually separated that way. Okay? Which is fine. It all still kind of pans out the same way. But let's kind of maybe do it this way. Now, the reason I would do that is you have now, and highlighting them might be a little bit easier to recognize, you have a fraction here divided by a fraction, correct? Now, algebraically, what would you do if you had a fraction divided by a fraction? How would you do that? How would you do that math? you take the reciprocal of the blue one and multiply, right? But in this case, because the denominators are the same, that process is ultimately just going to cancel those out and leave you the yellow numerator over the blue numerator, right? And that's kind of the shortcut when the denominators are the same. So what that leaves me with now is 1 minus cosine theta over 1 plus cosine theta. That's the tangent of theta over 2. Now, that's still kind of ugly. It's not the way it'll ever be described to you in a true cheat sheet for identity. Okay? It works fine. Okay? But what we find out is there is a really, really nice process that we can go through here of multiplying by a conjugate. And it really doesn't matter which one you use. Let's just go by what normally people are going to do is multiply by the conjugate of the denominator. That's usually what they're comfortable doing or what they've done in the past with other algebraic procedures. So let's multiply by that thing. When we do that, so we get plus or minus. Okay, what's 1? Now, you could FOIL this out. I'm going to tell you to be cautious of FOILing out and just rewrite it this way. Because those are the same thing, are they not? And recognizing that they're the same thing, that gives me a power of 2, which is nice because now they're both underneath the same radical, right? Okay. Now, this one here I am going to multiply out. This bottom one. Because they are what to one another? Conjugates. So what's going to happen? O and I are cancel out, right? So we're left with 1 minus cosine squared theta. Okay, so at this stage I'm going to do this. I'm going to separate the numerator and the denominator. Put them in the lower radicals. What is 1 minus cosine squared the same as? Sine squared, right? And now maybe you see the reason for this process of multiplying by conjugates, because when I do that, that thing right there is being squared and it's underneath the square root, right? What do those two operations do to one another? Cancel each other out. Inverses. So we get 1 minus cosine theta over, what's this power of 2 and this root going to do? Cancel out. So sine of theta. There is your tangent half-angle identity or half-angle formula. Okay? Now, you might see it that way. You might see an alternative way here. When we multiplied by conjugate, we had options. We could have multiplied by 1 minus cosine like we did, or we're going to multiply by 1 plus cosine. It would be the numerator's conjugate. If we would multiply by the numerator's conjugate, it would produce the same thing that I would get if I multiplied right here by the conjugate. Let's multiply this by the numerator's conjugate. And we'll multiply the top one out. I multiply the top one out, I get 1 minus cosine squared theta, right? The bottom one I am not going to multiply out. I'm going to leave it as sine theta times 1 plus cosine theta. Okay? What's the top turn into? What is 1 minus cosine squared the same as? Sine squared. And the bottom, like I said, I'm not multiplying that out. And the reason I'm not going to multiply that out is because I see that there's a sine squared up here and there's a sine in the bottom. What can happen there? One of those can cancel, and it leaves you sine of theta over 1 plus cosine of theta. So that right there and this red one right there are ultimately alternate versions of the tangent half angle. Okay? Alternative versions of the tangent half angle. Now, this is all in that cheat sheet that I gave you guys. Okay? If I look at that, okay, tangent of u over 2 is equal to 1 minus cosine u over sine u, is equal to sine u over 1 plus cosine u. Those are your formulas. Now, a lot of times, one of them is in regards to formulas that have like multiple approaches, like if we go to the double angle for cosine, didn't we say sometimes this one here would be better than this one? Because I can evaluate the cosine double angle just knowing sine here, right? To use this one, I got to know both. Well, down here, is this one any better than that one? Using in that regard? No. If I want to evaluate tangent, regardless of which version I use, I have to know the entire ordered pair of u. Okay? I need to know the cosine and I need to know the sine. Okay? So that is how those things are generated. Okay. Okay. So that being said, let's get to these practice problems. Then. Okay. So tangent of 3 pi over 8. Okay. 3 pi over 8. I don't like dealing with radians, and I'm going to make kind of a broad statement that I think you guys probably don't like dealing with them either, right? Or if you had an option, maybe you are comfortable with them, but if you had an option, wouldn't you much prefer degrees? So let's take this and go 3 pi over 8 and multiply it by 180 over pi. That will convert things, right? Okay. Let's take 3 times 180. Is that 540? 540 divided by 8 then is 135 over 2, which is 67.5 degrees. Okay. 67.5 degrees. So let's write it this way. Instead of writing tangent 3 pi over 8, let's write it as tangent of 67.5 degrees. Okay. That is much easier in trying to figure out how we're going to kind of fill in our formula than leaving it in terms of radian. Okay. Working with the radian process is problematic. So the reason I say that is because remember your tangent formula is always asking you for theta. Well, this right here is a theta divided by 2. Does that make sense? And here's the reason. This is the way maybe you can think about how to relate those or how to know if those go together. Do you know 67.5 off the unit circle? No. Okay? But if I rewrite that one more step, I'm going to rewrite that as tangent of 135 over 2. Does that make sense to everybody? Now, that's still theta over 2, but I like that, and I think people appreciate looking at it this way, because if that's theta over 2, what does theta have to be in this case? 135, right? Does that make sense? And why do I want to know that? Is because when I look at the tangent half angle formula, either one that you use, I'm going to use the one that says sine of theta is equal to 1 plus, or sorry, sine theta divided by 1 plus cosine theta. Okay? The theta now is the 135. Does that make sense to everybody? And the number one error I get with people using these formulas, the half angle formulas, is that they are unsure of whether they put the 135 in or they put the 67.5 in. Okay? One way of thinking about it, and it won't always work, but usually if you don't know the number that they're asking for, 67.5, I don't know if the unit circle, I'm not going to put that one in for theta, right? Now, like I said, that doesn't always work. They might be asking you, find tangent of 60 using 30 degrees. Both those off the unit circle. But I like to rewrite it as tangent of 135 over 2 here, so it gives me insight on what I'm really trying to evaluate here. So now we should know the sine of 135. What is the sine of 135? Radical 2 over 2. And then the cosine of 135 is negative radical 2 over 2. Okay? So now we've got that, and we want to just kind of simplify that. So I'm going to have, it'll be radical 2 over 2 divided by, it's going to be 2 minus radical 2 over 2, right? Okay? What's going to happen with my radicals here, or my denominators, I guess, those denominators are going to cancel, right? And we left with radical 2 over 2 minus root 2. And guys, I think, because WebAssign is usually pretty lenient with this, I think if you type that in, it's probably going to say, yes, you're right. I think if you type this in, it's probably going to say, yes, you're right. If I type those in and maybe I get them wrong, and I get this feedback here, you might be like, oh, I'm not even on the right page. I'm not even getting close to what I'm getting at, okay? But if we realize that we don't like this 2 minus root 2 in the bottom, what do I multiply to get rid of that 2 minus root 2? This is the algebra that we should have the conjugate. We multiply by 2 plus root 2. 2 plus root 2. And now when I multiply that out, I get 2 root 2 up top plus root 4, which is just 2, right? On the bottom, the reason multiplying by conjugates is because the 2 times 2 is going to give me 4. And then the negative radical 2 times radical 2 is going to give me minus 2, right? So it rationalizes that bottom, which 4 minus 2 is just 2, correct? Now, to cancel, is that 2 has got to be in part of every single thing up there. And it is. So does that give me root 2 plus 1 left over? Does that make sense? Okay. Now, Tyler, you gave me a thumbs up. Does that mean that is going to be accepted there? Okay. But I think it's important, guys, to be able to do all that algebra there, because even though they give me the answer when I'm wrong, if I don't know that algebra, I have no ability to get to that answer anyways, right? Just to have useful feedback. Okay. So I need to know that the versions that we are typing in that may be wrong can be converted down to something like this. So, maybe if I had a plus sign right here or something like that, I could convert down and see that maybe that jacks this set of numbers up, but they're in that same structure. Okay. That's how I would approach that question. And you would do the same thing, guys, then if that was a sine or a cosine. Obviously, then you just use a different formula, right? So what other ones do we talk about? Fanny? 2 on assignment number 2. Okay. So I will, let's skip this now. Okay. I will, because we're going to run out, and I want to make sure we get the half angle, double angle stuff in. But this comes from this as well. I mean, cosine of 2x equals 2 cosine squared x minus 1. Okay. If I go ahead and start solving this stuff right here for just cosine squared of x, it's going to look like this: cosine of 2x plus 1 all over 2. Okay. What this does is it takes when you start with a power of 2, does it end up rewriting things in terms of a power of 1? Okay. If I open up cheat sheet here for you real quick, here you see formulas for lowering powers. It's cosine squared x equals 1 plus cosine 2x over 2. It's exactly what we have, right? Okay. Then what we see, I guess we can do this. It's not, now we have this, it's not a huge deal. Isn't cosine of 4, or cosine of the 4th of x the same thing as cosine squared x times cosine squared x? Okay. So then we could have cosine of 2x plus 1 over 2, okay, then times cosine of, this is plus 1 like that, cosine of 2x plus 1 over 2 that way, Okay. I'll work through to multiply that out. So that's going to give me cosine squared of 2x, correct? Okay. And then plus 2 cosine of 2x plus 1 all over 4. So I'm going to pull that 1/4 out like this. Okay. Now the next thing is this cosine squared. We got to do one more iteration of getting rid of that, right? So that is, so we're going to have 1/4 cosine squared of 2x is the 1 plus cosine 2x. So I'm just going to write it's cosine 2x plus 1 over 2, and then plus 2 cosine 2x plus 1. Okay. I keep doing that, that plus 1 in the argument. Shouldn't be that way. Say again? Because that's the cosine power reducing formula is the cosine of 2x plus 1 over 2. That is the same thing as cosine squared x. So it's just got to be over 2. And that, now obviously that's not the same as what we're seeing here, okay? But if we were to type this into GeoGebra or something like that, or Desmos, they would be identical, and it will accept that, okay? But in regards to saving time, let's come back on Monday. So let's extend this one beyond Monday. Let's come back on Monday and talk about the power reducing. To be honest with you, I didn't realize I had one of those in there. We'll go to power reducing formulas on Monday, and maybe the sum to product and product to sum formulas on Monday. But let's kind of focus more on the half angles. Are there any more half angles that you guys want to talk about? I know the last class had this question. I think it's 18 or 19. These are some of the products. Okay, so those are maybe ones that we don't want to do right away. And the reason we know these are some of the products is because notice the arguments are different, right? The ones in the homework that you see the arguments being different, kind of wait until Monday, and we'll address those on Monday. So that's okay. So there's a half angle. We okay with those? I mean, I can do whatever you guys want to do. Want to do one of those? You remember yesterday we did the double angle, right? We drew a picture. This is the exact same question, type of question. Draw your picture for tangent of theta being negative 5/12. Theta is in quadrant 4. So when I draw this, okay, tangent in quadrant 4, or theta is in quadrant 4, tangent is negative 5/12. That makes this 13, doesn't it? No, sorry. Because the 5 is the... Yeah, I'm sorry. That does makes that 13. Okay, so 12 squared is 144. 5 squared is 25. That's 169. Square root, there you get 13, right? Okay. This just says assume that theta is between 0 and 2 pi, so 0 to 360. So we're not talking about an angle that's like 400 degrees or anything like that. Does that make sense? Or I guess it'd be 600 degrees if we're in the fourth quadrant. Okay. Now, here's the thing. Here's what we've got to kind of pay attention to. If we are in the fourth quadrant, our angle is going to be between 270 and 360, right? If you take 360 and cut it in half, take 270 and cut it in half. What is 270 cut in half? 135, isn't it? Which would be maybe that ray right there. Okay. What is 360 cut in half? 180, which is that ray right there, right? So our angle that we're talking about, if we're going to trace it out, our half angle is going to be somewhere in between those two red rays. Does that make sense? And that's nice because now it tells me the plus or minus that I have to choose for the sine value. Does that make sense, everybody? It's going to be the second quadrant. When they say sine of theta over 2, it's now a second quadrant angle. So I know I've got to have a positive value for my sine. Okay? So now, if sine of theta over 2 is what we're looking for, the sine of theta, that's plus or minus the square root of, now it's 1 minus cosine of theta over 2. Okay? Theta is this blue angle, right? So I'm going to go plus. That'll be 1 minus the cosine of that blue angle. The cosine of that blue angle is 12/13, right? All over 2. Does that make sense? Now we've got, this is going to be 13, so I get 1/13 divided by 2. That's all underneath the square root, right? I'm going to multiply by that fraction of 1/2, that reciprocal of that. So it gives me 1 over 26. Those are both in a root, right? So do you see where we're getting then root 26 over 26 after we rationalize? And we should be able to check that. We should be able to take our calculator, if we understand our K83 or Desmos well enough, we will check this, or GeoGebra. I'm going to use GeoGebra because it's going to give us a picture as well. But let's go ahead and see this real quick. If I know the tangent, and we got to do a little bit of work here. If I know the tangent is negative 5/12, this thing froze. There we go. The tangent it was negative 5/12, right? So the arctangent of negative 5/12 is going to give me an angle of negative 22.62, right? I want to take that, okay, and I want to add 360 to it, don't I? Whoa. I don't know what that's doing. Let's do it this way. So we're going arc tangent of negative 5/12 plus 360. I don't know if I need to put a degree in there or not. No. Okay. That's not right. Arc tangent, negative 5/12. And this is just knowing the syntax of GeoGebra here. There we go. Okay. So that's the angle they're talking about when they say that tangent is negative 5/12 and we're in the fourth quadrant. Does that make sense to everyone? Okay. So now if I just draw this circle in here, we had x squared plus y squared. We had a radius of 13, so 169 would be my circle. Okay. If we look at that angle of 337.38, we're going from A to B. We're going alpha, and we want to go counterclockwise, so put that in there. It gives me that angle. Does that make sense to everybody? So when it gives me that angle, we now have from this point here to there, we drop down that perpendicular line to get that intersection point. So we're talking about now that triangle. Is that okay with everybody? Okay, so that triangle, then if we look at that distance, it's 12, 13, and it should be a negative 5 in this case. Now, here's the thing. If I take half of this angle, and really, the picture is nice to see, I think. We want half of 337.38. Does that make sense? So if I were doing this on my calculator, I don't necessarily need to draw all this picture stuff. When we go the sine of 337.38, okay, divide that by 2, it gives us that number right there. Is that okay? Okay. Now, if I look at why does it give me a negative? I think it's because, let's do it this way. Let's go over 2. Is that number right? You guys agree that's the second quadrant? So the y value should be positive, right? So if I say sine of gamma now, hit enter, we get the 0.2. Okay? What this is doing right here. The negative 0.82. So 0.2 is the sine of that half angle, the half of this 337.38. We found it to be exactly the square root of 26 over 26. We're going to see if that's the same 0.2 number, and it is. Does that make sense? So that's kind of how we check ourselves. If we're using just their calculator, just Desmos, okay, like I said, you have to be able to understand what's going on when I tell you the tangent of x is equal to negative 5/12, and we're in the fourth tangent of negative 5/12 then gives that number right there, and as a degree, it ends up being that degree. Now we know it's a fourth quadrant angle, so we never like to write it as a degree, so we go plus 360, right? So there's the angle we're talking about. That's the theta. That's the theta that's being talked about right here. Does that make sense? Okay, we should always be able to find that. If they give me what the tangent of theta is equal to as a ratio, or the sine of theta equal to as a ratio, if they give me the ratio, I should always be able to figure out the angle that they talked about. Now, if I take sine of that angle, 337.3801355052, and divide it by 2, there's my half angle, right? That should be the same thing then as the square root of 26 divided by 26, and we see that it is, right? Okay? So my whole process here, I think obviously checking it is actually a little bit more work than solving for it. Finding the answer, I think it takes a little bit more time. But the more you do it, the more you force yourself to kind of understand that check, the quicker you're going to get at it. And the more, I guess, efficient you're going to be at checking it. And it'll almost be almost instantaneous that you know what to do, when to do it, and validate your answer. Okay? I think the key thing that maybe something people overlook is the plus or minus, not knowing what quadrant you're going to be in. But if I know that we're in the fourth quadrant, the fourth quadrant is segmented by 270 and 360, those are kind of the back. Then if the angle they provided me was right at 270, then half that would be 135. If the boundary they provided me is right, the angle is right at 360, half that is 180. So then if I'm in between somewhere, then I got to be between 135 and 180 as my half angle. I think that's a key concept to kind of understand. So that question, guys, can be asked with any sine, cosine, or tangent half angle. They can produce or provide you with any tangent, sine, cosine of theta equals some ratio. And they can tell you in any quadrant, right? So there's a lot of different variations of that problem, but you approach them all in a very, very similar way. Okay? Same stuff there with we did now I don't like this because they tell me cotangent of x equals 8. So what would I rewrite that as? Tangent of x equals 1/8. Okay. Now, if I'm between 180 and 270. So now I'm here or there, right? So that's where my theta is. That's my triangle right there. Would be tangent is opposite over adjacent. So -1, -8, right? Okay. I'm going to add those together. Doesn't that give this to be 3? Is that right? -1 squared. No, sorry. I'm an idiot. Be -1 60%. So root 65, right? So that's going to be that hypotenuse. Now remember, so this is 270. This is 180, right? So my full angle theta or x exists in those two kind of demarcation lines, right? If I take half of 180 and half of 270, half of 180 is 90, half of 270 is again 135. So my x over 2 is going to rest somewhere in between that red ray, right? My angle of x over 2 is going to be somewhere between 90 and 135 degrees. Okay? So that tells me then that when I choose the sign, look at the overall value of the sign, positive, right? When I choose the cosine, because in that little red angle, it's in the second quadrant, right? So that's why the cosine is negative. And then if we do the tangent is going to be negative as well. These are then those exact values, okay, that we would type into our calculator for. And then once I evaluate, we want to take our tangent of 1/8 and get an answer back, take half of that. That radical should equal half of essentially the sine of the arctangent of 1/8 divided by 2. Okay? Keep working on those. I'm going to push them back. Okay, so that's 7-1. I'm going to push back to Monday at midnight. Okay, so please make sure we're working on that. Now, I've been lenient for a lot of classes. Been lenient with pushing back homework lately, right? Okay. A lot of people came in and said, "Hey, Mr. Peck, can you push that back today? Push that back today, please, please, please." It's been open for a week, and they have not even opened it. Okay, and I can see the logs that they do. Every time you click on something, it tells me the timestamp of what you click on, when you did it, all that kind of stuff. And they haven't even opened it yet. Okay, so they don't have the argument that we got the top covered in 7-3 day 2 yet, right? But how would they know that? They haven't even opened it. Okay, so if I'm going to push things back, guys, I was going to push this 3 back because there are questions on there we can't do yet. So 7-3 day 1. I shouldn't be pushing that back, especially if you haven't opened it. Okay, you have no argument there. Now, I haven't looked at your guys' because nobody really asked me to push it back yet in this class. But I am going to push it back to Monday at midnight for 7-3 day 1. Day 2, I'm going to push back to Tuesday at least, and we'll get through those. The sum of product sum formulas are not hard. The power reducing formulas are not hard. Say again? I don't know if it's been, but it was, let's see here.